Good morning everyone. Today our group will be presenting on computer architecture, CPU functions and parallel processing. We will be covering major topics such as CPU structure, instruction execution, performance, pipelining, superscalar processing and pins classification. Our group members are Niven, Kitmini, Lakidu, Hasaranga and myself, Warati.
Right. First of all, we have to know basic structure of computer system. We describe the basic structure of computer system. A computer consists of 5 main functional units. First one is input unit, which takes data into the system. Second one is output unit, which display or transfer process results. Third one is memory unit, which store both instructions and data. Fourth one is ALU. ALU means arithmetic and logical unit, where all arithmetic and logical operations occur. Fifth one is control unit, which manages and coordinates all operations in the CPU. Together, these all units allow the computer to accept input, process it, store information and generate output. Okay, the first part is over. Let's move to the second part. Fetch, decode, execute cycle. Okay, I will be describe about fetch, decode and execution cycle. So the CPU works through a repeated sequence called the fetch, decode, execute cycle. First, the fetch step. The CPU retrieves the next instruction from memory using the program counter. Then the decode stage. The control unit interprets what the instruction means and determines which components are needed. Next, third step. This step is execute stage. The ALU performs the required operation, such as addition or comparison. Find the result when written back to the register or memory. The cycle repeats continuously as long as computer running. So let's move to the next part. Okay, this part I explain data transfer between CPU and memory. There is a 3-bus line: address bus, data bus and control bus. Data transfer between CPU and memory happens using the bus systems. The address bus selects the memory location that the CPU wants to read or write. The second bus line is data bus. The data bus carries the actual data between CPU and the memory. So third bus line is the control bus. The control bus handles read or write signals to coordinate the transfer. There are 3 buses work together to ensure a smooth synchronized communication between memory and the process. Okay, next move to the next part. The next part is von Neumann versus Harvard architecture. That part will be present Kitmini Jaiswal.
Thank you, Nive. There are 2 major CPU architectures, Harvard and von Neumann. In von Neumann architecture, both data and instructions share the same memory and bus. This makes the design simpler but creates what's known as the von Neumann bottleneck, because only one operation can happen at a time. In contrast, Harvard architecture uses separate memory and buses for data and instructions. This enables parallel access and improves performance, which is why it is commonly used in microcontrollers and DSP systems. Next part is factors affecting performance. Several factors affect the performance of a computer system. First one is clock speed. Higher clock rates mean more instructions can be executed per second. Second one is number of cores. More cores allows better multitasking and parallel processing. Third one is cache size. A larger cache reduces delays caused by memory access. Fourth one is memory speed and bandwidth. Faster memory ensures quicker data delivery to the CPU. All these factors together determine how efficiently a computer can handle tasks. Next part, Niven will be continue.
Okay, I will explain CPU design steps. There are three main steps: instruction set architecture, data path, control unit. Design a processor involves several important steps. First, we define the instruction set architecture, which tells the CPU what is capable of doing. Next, we will build data path, which include registers, the ALU and internal buses. Then we next move to the design the control unit, which generates the signals needed for each instruction. All that components are integrated together. Finally, we optimize the processor of performance, cost and power efficiency. Okay, next part is instruction set and its impact. This will be explained Lakindu Ransika.
So now I will talk about instruction set and its impact. The instruction set determines what operations a processor can perform. It heavily influences the CPU internal structure because the data path and the control must be designed to support each instruction. A complex instruction set increases hardware complexity but may reduce the number of instructions needed for a task. A simpler instruction set reduces complexity but may require more instructions. So the ISA plays a major role in processor performance and efficiency. So now I am going to talk about instruction types. Instruction sets generally include four main categories of instruction. First, arithmetic instruction such as add or sub. Second, data transfer instructions like load or store. Third, we have a control or branch instruction such as BEQ and jump, which modify program flow. Lastly, we have logical instruction such as AND or OR. These different types allow the CPU to handle computation, data movement and decision making. Okay, now after instruction types, I am going to talk about single cycle processor. A single cycle processor completes every instruction in exactly one clock cycle. All components such as ALU, memory and control unit must operate within that single cycle. This makes the design simple but also inefficient because the clock cycle must be long enough to accommodate the slowest instruction. As a result, faster instruction waste time waiting for the cycle to finish. So now I will hand over to Hasaranga.
I am going to explain about what is pipelining. Pipelining is a technique used to improve CPU performance by dividing instruction execution into separate stages. These stages typically include instruction fetch, decode, execute, memory access and write back. Each stage processes a different instruction simultaneously, similar to an assembly line. This allows multiple instructions to be in progress at the same time. So let's move on to next part. How pipelining improves performance. With pipelining, the CPU increases throughput, the number of instructions completed per unit time. Although the execution time of a single instruction doesn't change, multiple instructions overlap and complete faster. Hardware is used more efficiently as different stages work in parallel. In ideal cases, pipelining achieves close to one instruction completed per clock cycle. Okay, next part will be described Kitmini Jayashree.
Let's move to superscalar processors. Superscalar processors take pipelining even further. They contain multiple ALUs and multiple pipelines, allowing the CPU to issue and execute more than one instruction in a single clock cycle. This dramatically increases speed and is used in the most modern processors like Intel and AMD chips. In contrast, scalar processors can only execute one instruction at a time. Let's move to Flint's classification. Flint's classification categorizes computer architecture based on the number of instruction streams and data streams they handle. First one is SISD, single instruction, single data, traditional single core CPUs. Second one is SIMD, single instruction, multiple data, used in GPUs for parallel operations. Third one is MISD, multiple instruction, single data, rarely used. Fourth one is MIMD, multiple instruction, multiple data, found in multi-core processors. Last one is FPMD, single program, multiple data, widely used in parallel programming.
Now we'll see real-world examples for Flint's classification. Here are real examples for them for SISD, single instruction, single data, where standard laptops or desktops will be using single core CPU. Single instruction, multiple data is used in graphics processing units used for gaming and AI computations. Multiple instruction, single data is used rarely, but in CPUs such as in Intel i7 and AMD Ryzen. Multiple instruction, multiple data is used in parallel computing frameworks like MPI, where processing units run the same program on different data. So by that we concluded our presentation. So in summary, we covered the basic structure of a computer system, the fetch, decode, execute cycle and CPU memory interactions. We also compared Harvard and von Neumann architectures and explained its performance in factors. And also we discussed how processors are designed, how instructions shape the architecture, and how modern CPUs use pipelining and superscalar techniques for speed. Finally, we reviewed Flint's classification and its real-world examples. So, thank you for listening.